A slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. Okay. Hannah, what's A want me to find? So a lot of students don't write this down. They do this. They go, oh, potential energy equals mgh because that's what it says on your formula sheet. But that's gravitational potential energy when you're lifting something. Are you lifting something here? No, but here's what they do. They panic and they go, oh, there's the mass, Mr. Dueck. So they stick that there, 9.8 h, that's meters. Oh, that must be a height. But look at this. Is that vertical? Is that a height? Don't do that. That's a hint for either the bow and arrow question or the slingshot question. Instead, I think we're going to have to think force times distance and work because they did give me a force and they gave me a distance. Now, the first thing, of course, Hannah, I would say, nice try, Dueck, and I would make that 0.9 meters. So, how can I calculate work, which is going to be the potential energy stored? It's going to be force times distance. It's going to be 70 times 0.9, Hannah, which is what? Yep. Oh, not newtons, Mr. Dueck. This is work and energy, joules. That's how much energy was stored in the slingshot. Where'd that energy come from, by the way? Your body, whoever was pulling this, their body has lost some energy. Where'd that energy come from? The food that they eat. Energy's always got to come from somewhere. It's got to go somewhere. If there's a 35-gram, nice try, Dueck. Grams, it's divided by 1,000 because it's kilograms. So it's 0.00, no, not 0.00, 0.035 kilograms. How fast will it leave the slingshot? So this is a job for conservation of energy, but I'm going to simplify it a little bit. I could write down PE initial plus KE initial equals PE final plus KE final. There isn't a change in height. There isn't a change in speed. There isn't the yucky curvy path, but I do have some potential energy. What's it turning into? What type of energy? Kinetic. That's your hint that this is a conservation of energy question. So I'm just going to argue this. All of the initial potential energy turns into the final kinetic energy. That's my argument. And that's the case for a slingshot or for a bow and arrow. Um, it's going to be 63 equals a half mv squared. Now I'll write it as mv squared over 2 because that's easier to get the v by itself. Hannah, let's finish this off. How would I get the v by itself? How would I move the m over? Okay, I'd multiply the 2 over, and then how would I move the m over? Divide, and that would give me a v squared. I'll write that so that we know in our notes what the heck we did. I would have v squared equals 2 times 63 divided by m. Now, how do I get rid of a squared? This might work out. I'm doing some quick math in my head. Is this going to work out evenly? It's going to be 2 times 63 divided by 0.035. It might. Maybe not. I'm just seeing a 7 canceling, and I'm seeing a 9 left behind. Hannah, what'd you get? Sorry? 6-0? Okay. That's a fluke that it worked out evenly. Don't count on that. But that seems reasonable to me. When I was a kid, we had slingshots. When I was a kid, we had a cabin up near 100 Mile House. And so every summer when we went there, the first day, my dad would, I have 2 brothers, so he would walk the 3 boys into the woods and he would carve us slingshots and he would make them, we would sit there watching, fascinated as he made us all a slingshot. For the next 2 weeks, we were firing rocks and everything. So slingshots are dear to my heart. So 60 meters per second, is that fast? That's faster than you can throw it, but that's not bullet fast. That seems ballpark reasonable to me for a slingshot. That would be about half of the football field in 1 second. That's fast enough. I wouldn't want to get hit by it, but I could follow it with my eyes. I could see the blur of the rock. That seems. I don't think we've made a mistake. That's my point. Okay. Another great example of conservation of energy are rope swings. So Tarzan weighs 82 kilograms. It can run at 8 meters per second, 80 meters per second. Not even Tarzan could do that. He runs along the ground, grabs a vine swinging into the air. What maximum height does he reach? And then it says DOLP. Does anybody remember what does DOLP stand for? Draw a little picture. I'm going to do a little bit of a DOLP here. So I'm going to have, here's the ground. Here's Tarzan running. That's about as good as you'll ever see me draw a picture. Here's the vine. And I think Tarzan's going to swing into the air, something like that. Fair enough? Okay. Evelyn, let's plan our attack. What does it want us to find? Height. Okay. Is there a change in height? Will there be a change in speed? Is there a yucky, curvy path? This is definitely a good job for conservation of energy. So I'm going to start out by writing the full thing. K E initial plus P E initial equals K E final plus P E final. And then, Evelyn, we always asked, are any of these zero? Kinetic energy will be zero when Tarzan is at rest. Will there be a place that Tarzan is at rest? I think so. Where? Good. At the very, very top, I heard somebody whisper. Yeah. Is there ever a place where Tarzan is on the ground? Where? Now, someone pointed out last time I taught this that, wait, Mr. Dueck, that's not on the ground. That's high off the ground. Here's one of the lovely things about the law of conservation of energy. We can put our height of zero anywhere we want. I'm going to put our height of zero right at the bottom of the vine, and I agree. I'm going to call that zero. Let's expand this. What's the equation for kinetic energy, Evelyn? I'd like to think it's a half mv squared, and initial would be initial. And I think potential energy, gravitational potential energy, is mgh final. Oh, I noticed something. Evelyn, is there an m in the first term? Is there an m in the second term? What does that mean? Yeah, what it means is not only will Tarzan swing up to this height, but if Tantor the elephant could run at 8 meters per second, and if the elephant grabbed the vine, assuming the vine didn't break, they'll both swing up to the same height. Yeah. I I don't know. I did not grow up in Pitt Meadows. Is there a good rope swing over water in Pitt Meadows somewhere that everyone knows about? No? Okay. So growing up in Abbotsford, there was one out in Hope that we all knew about on Cockaway Lake, and we would go there. And you would notice it didn't matter how heavy a person was. All the people swung out to pretty much the same height because they were starting from the same spot, and the masses were canceled, and they were all ending up at the same height, whether it was a kid or an adult, someone heavy, someone light. If they gave themselves a bit of a push by adding some extra energy, they could go a tiny bit higher. But the way it was set up, you couldn't give yourself a big push. It was kind of lift your feet up and swing out. Okay. What are we trying to find? Let's get the h by itself. Oh, I like the way you wrote that. You ignored the one. Yeah, that was nice. It's going to be the VI squared is going to drop down like a domino. There's a 2. I'm not going to bother putting the 1. There's going to be a G. And then do you mind, Evelyn? I'm going to put the H equals on that side. Yep. It's going to be 8 squared divided by 2 times 9.8. By the way, oh, let's crunch that first of all. Let's see what we get. 3.26. Anybody else? Oh, you didn't make a rounding off error after correcting me yesterday, did you? Um, if Tarzan ran twice as fast, how many times higher would he go? If he ran twice as fast, how many times higher would he go? Yeah, 4 because of the squared. This goes back to what I talked about a couple of days ago with sports equipment, where you're trying to achieve distance by hitting something. You make the mass lighter to get faster speed because you get more bang for your buck by doubling the speed than you do by doubling the mass. Yeah, 4 times further. I didn't need to do the math. I could just see the squared. Yep. Okay. Slap shots are great examples of energy transformations. I'll show you the video at the end, though. I want to make sure we get through the lesson. And besides, here's a roller coaster. Roller coaster below has a mass of 255 kilograms. If it just makes it over the first hill, how fast will it be going at B? So we've done one like this already. What I said to you was I tend to put the initial and the final right on the diagram. How am I going to solve this? I know it's saying how fast. I'm not going to use VF equals VI plus AT or D equals VIT plus a half AT squared, because those are all vector equations. Ryan, is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is where conservation of energy really shines. So I'll start out by writing out the equation K E initial plus P E initial equals K E final plus P E final. Mr. Dueck, if I know some of these are 0, do I need to write them in your homework? No, I'm doing notes though, so that when you're studying, you know what the heck we're doing. Rye, are any of these 0? What? Okay. And then I think just barely makes it over the first hill. I think we're supposed to assume that's their hint that it's that. I'm gonna, oh yeah, it says assume VI equals 0. Okay. And in fact, we get pretty much the same equation that Evelyn just did with us, except here it's the initial potential and the final kinetic, but we're getting one thing equals one thing. We're going to get mgh initial equals a half mv final squared. Here I'm asking you to find the speed, but also I would have no problem giving you the speed at the bottom and asking you to find the height of the hill. To get the can little kids and grown-ups go on roller coasters together? Yeah. Again, don't take that for granted. The fact that that happens is actually really important. Next year, when we start analyzing traffic and looking at roads, we'll also find when we look at when cars going around a corner, the masses cancel, which is hugely important. Otherwise, semi-trucks would have to have different road systems than cars. Cost us a fortune. We'd have to have a completely separate traffic infrastructure for anything. Or what we would do, Jackson, is build all of our cars one mass, all of our big trucks another mass, and just have 2 separate road systems. But even that would be crazy. Uh, I'm going to go, well, how would I get the V by itself, right? Times by 2. Now, that gives me a VF squared, square root. It's going to be the square root of 2 times 9.8 times, what was H, 18? Looks like a decimal point there. Let's get rid of that little splotch. What'd you get? If you double the height here, how much faster will you go? Okay. The answer is you'll go root 2 as fast because you're adding an extra 2 inside the square root. You'll go the square root of 2 times as fast. So doubling the height does not give you the same bang for your buck. You'll go faster, not twice as fast. If you're wondering, well, what is the square root of 2 on your calculator? No, the square root of 2. You'll go 1.414 times as fast, not twice as fast. If you triple the height, you'll go root 3 as fast, which is about 1.7 times as fast. So getting roller coasters to go fast, higher hills do make a difference, but I was on Six Flags Magic Mountain has one called Goliath, which for about 5 years had the world record as the highest hill. And it's great because it lasts a long time, but you're not going significantly faster than some of the coasters that have not as high a hill. It just doesn't make as big a difference. Yeah, 4 times as high would give you twice the speed. Yeah, because you get root, the square root of whatever the factor is, because it ends up inside the square root to begin with. I'm not going to be quizzing you on that. This is just nerd trivia, because if you haven't figured out, I like roller coasters. Suppose the coaster had an initial speed at part A. Now how fast will it be going? Jordan, it's going to be the same setup as before. Change in height, change in speed, yucky curvy path, yes? But this time, Jordan, the only one that's zero is that one. My initial is not zero. Okay. So it's a little more work. I'm going to replace the KE with a half MV initial squared, MGH initial, and a half MV final squared. Oh, Jordan, can little kids and grown-ups go on this roller coaster? How come? That's good. Again, if that didn't happen before you got on a coaster, they would have to have you step on a scale and they would have to spread out all the masses and oh, we can't go any more than this and won't make it through anymore. What are we trying to find? Yeah. You can, if you want to, divide by 0.5 square root. For what it's worth, because I know some of you are doing this in math right now, you could also choose to go times by 2, times by 2, times by 2. You can clear fractions. And what's neat about that is you get our old friend vi squared plus 2gh equals vf squared. This is vf squared equals vi squared plus 2ad in disguise, which is kind of nice. And then square root. But I have no problem if you're not comfortable with clearing fractions, Jackson. If you want to go divide by 0.5 and then square root, you'll get the same answer. I just like that equation pops out of there. What was the initial? 22 squared plus 2 times 9.8 times 18. Jordan, what do you get this time? Should be definitely going faster because we had way more energy, kinetic energy especially, to begin with. So definitely going to be going faster than the 18.9. Mr. Dueck, can't I just go 22 plus 18.9? Will that work? I don't think it will. I don't think you got 40.9, did you? We still have to do the numbers. What'd you get, Jordan? It's going to be bigger than 22. I can tell you that. 28.9. Anybody else? No, yes? Oh, yeah, 28.9. So even though we're going way faster over the first hill, Jordan, not that big a difference at the bottom. And it's again because of that squared. Was it 28.9? I mean, that's better. Just for context, 18.9 times 3.6 68 kilometers per hour. Okay, that's about around what the Playland wooden coaster does. The wooden coaster at Playland is scary because you can feel the infrastructure moving because it's wood, and that adds to the thrill. And it's just a lap bar as opposed to shoulder harnesses, so you get thrown against the lap bar when you go over, and that's part of the thrill. And oh, good ride. It's considered a classic coaster. 28.9. That's a little better. I'll stand in line for that. I've been faster on a roller coaster. Turn the page. Suppose the coaster in part B is only traveling at 25 meters per second at the bottom. How much energy was lost to heat? Ooh, okay. Angus, I'm pretty sure we're using energy because it says how much energy. It's going to be conservation of energy, but now they want me to include heat. So I'm going to take my conservation of energy equation and I'm going to include heat on the right-hand side because apparently some of the extra energy went there. Thermal. I think we can still do that. Bottom. But we're in part B. Part B was kinetic energy initial 0. I don't think it was. Okay. What do they want us to find? Get the heat by itself. How would I move the KEF over? Yeah. And this is a weird one. I don't know why. Because it's to me pretty clear that the KEF is adding on to the heat. Every year I see kids divide by KEF. A few of them. I haven't figured out why. They don't do it anywhere else. It's just this equation here. Don't do that. So you're telling me, and I think you're right, heat is going to be KE initial and PE initial minus KE final. Heat is going to be a half mv initial squared plus mgh initial minus a half mv final squared. Do the m's cancel this time? There's not a mass in heat. And so, Jackson, I'm fibbing a bit when I say the masses cancel. But what do we do in real life? We make the heat as close to 0 as we can. We grease the coasters down. They're not frictionless, but they're pretty good. Okay, now it's going to be plug and chug. I'm going to have to look at some of the numbers from the previous page. I'll scroll back so you can see the numbers. Mass is 255, height is 18, V is 22. Let's see if I can remember all that. 0.5, 255, V initial was 22, don't forget the squared, plus 255 times 9.8 times 18 minus 0.5, 255, and 25 squared. We know what you get, Angus. Take your time. So just over 27,000. I think that's right. Is it just a tiny bit above 27,000 joules? Oh, people are still typing. I'll round to 27,000, just to 3 sig figs, but if that's right. Anybody else get that? Maya, you got that okay or not? Yeah? Got a nod? Anyone else? I need another nod and then I'll know we're good? Yeah? Sure. So and I think I said this yesterday, that's wasted energy. Electric vehicles, because normally in a internal combustion engine car, when you step on the brakes, you're generating heat. You're losing kinetic energy. It's all going into heat. Electric vehicles, they bleed some of that away into their regenerative braking. It's why electric vehicles, especially hybrids, get such good gas mileage in the city. It's why all the taxi cabs went to hybrid vehicles, because every time they're stepping on the brakes, they're actually recharging their vehicle. A friend of mine has an electric car, and he started out at the top of the Coquihalla Summit on the Coquihalla Highway, and he ended up with more battery power at the bottom, even though he'd just driven for an hour and a half, because, oh, conservation of energy. He was losing potential energy. It's got to go somewhere, went into his batteries. Example 4, a cart and rider start from rest. I would probably underline from rest on a 20-meter high ramp. At the bottom, the car is traveling at 15 meters per second. How much energy is lost to heat? You know what? I think this is very similar to the question that Angus and I just did. It's going to be conservation of energy. Now, there is a change in height. There is a change in speed. There isn't a yucky, curvy path. But Anderson, are they talking about heat? Conservation of energy. This is a little nicer than the one Angus and I did. What's zeros here? Sorry? KEI and PEF on the ground. Nathan, how would I get the heat by itself? How to move the KEF over? Yeah. Heat is going to be PE initial minus KE E final. Heat is going to be mgh initial minus a half mv final squared. You know what? M's don't cancel. Be bold. See if you can go straight to your calculator without writing out the numbers. We'll try that. I think you got enough information there. 6,262, 6262. Is that what it is on your calculator? 6262 point what? Okay. 6262.5. Uh, because we're going to use this for part B, trust me, I'm going to write out the whole thing. 6262.5. Heat, units, joules, energy. Holly, what's B want me to find? Don't write this down, look up. My first thought would be, oh, this is easy. Friction equals mu times the normal force. Why doesn't that help me at all? No coefficient of friction. And also, we're on a slant. We'll talk about being on slants next year on ramps, but the normal force is not mg. We can't do that. So my next thought would be, well, maybe I'll use my previous answer. What did we just find, Nathan? Now, you know another word for heat? You can make a little note if you want to. Heat is the work done by friction. So I would start part B by saying the work done by friction equals force times, oh, which force? Take a guess. Yeah. Holly, how would I get the force of friction by itself? How would I move the D over? So I'm going to get this. The average force of friction is going to be the work done by friction, heat, divided by the distance. What's the heat? 62, 62.5. Ooh, which distance am I going to use? Am I going to use the 60 or the 20? Why? Because for work, the force and the distance had to be in the same direction. If friction is acting along the ramp, I better use the distance along the ramp. So you should be able to just go answer button divided by 60. 104 units, it's a force. Yeah. So this is actually kind of nice. We don't even know the coefficient of friction, but we can tell you what the average force of friction. And why did I say average? I suspect it's not constant. This might be because it's a straight ramp, but on a roller coaster where your angles are all changing, it changes. But you could certainly find the average without too much difficulty. Rube Goldberg machines are great examples of energy transformations. I think I told you Rube Goldberg was a cartoonist who used to draw elaborate chain reaction machines. I think it was for the Saturday Evening Post for their back page, and people really loved them. They were always very, very elaborate. So they're also called chain reaction machines. You can spot the energy transformations in this video. Put your pencil down, look up. This is going to be mostly potential into kinetic. And I think this one here, you want to follow the blue marble. Come on. So lots of, this is on a slant, not vertical, but you can still, you're getting potential energy turned into kinetic energy. But also there's all sorts of little stored energy, whether it's magnetic energy, elastic energy. So a little more elaborate than my little frigid contraption behind me on my board, but lots of fun to watch. You were going to say something or not? Yeah, we're going to get to that at the end. I haven't forgotten. A bouncing basketball is a great example of the law of what do you think C of E is an abbrev for? Yeah, I'll do that in the notes as well and in the homework. So at the top of the bounce, what type of energy does the ball have? Yeah, technically gravitational potential. So I'm going to say grav PE. Uh, when it hits the ground, what type of energy does it have? I noticed that if I just let a ball bounce and don't touch it, it loses height on each bounce. Does that violate the law of conservation of energy? Cody, how not? You're right. Where is the extra energy going into? Where is the missing energy going into? Okay, so no, energy goes into sound and more than you realize into heat. Do I have any basketball players here that played grade 8 or 9 or 10 or senior ball? Okay. I coached for many years. On Saturday morning, you would get the ball because, especially if you left the basketballs in your car overnight and your car was cold, they would be all flat. So the first thing you would do is you would give them to the players, and they would just pound them on the gym floor as hard as they could. You were adding heat to the basketballs to get the air to warm up to expand, so you could dribble them properly. So absolutely doesn't violate that. So here's the question: if I just drop a ball, is it possible for the ball to bounce higher than it was originally dropped? Yeah, Maya. I'm going to drop it. A golfer wants to hit his or her drives further by increasing the kinetic energy of the golf club when it strikes the ball. Because what you're doing is then you're passing some of that energy to the ball. What would have a greater effect? Doubling the mass of the club head or doubling the speed of the club head? Why? Yeah, doubling the speed will give 4 times as much energy because of the squared. Okay. What's your homework? I'm going to kind of really target certain things. I think what I'm going to do, 4 is pretty good. Roller coasters. There's going to be a roller coaster on your quiz. 5 is good. Ooh, ski hills are great examples of conservation of energy as well, as are water slides. 8 is good. Another water slide. So far I've assigned 4, 5, 6, 7, 8. I skipped 1, 2, 3, right? And you're probably going to get, let's see, yeah, 10 and 11. Okay. Let me hit pause.